So let's go on to the next step. Let's just remember where we are and how we're getting there. Of course, our ultimate goal is to learn how to convert points from one coordinate frame to another, regardless of how the two coordinate frames are set up relative to one another. We started by just looking at translation. And after we figured out how to do the translation, just to figure out what the translations were, we talked about the 4x4 matrix that represented a translation for our F frame transform that was also the equivalent of the T transform the other way. And that allows us to compute to transform points actually. So take a point that's fixed in space and figure out where it is relative to different coordinate frames. At this point, we've also talked about how do you do a transformation if you just have a single rotation of a frame. So no translation, but just a single rotation. And so you probably were expecting this. The next step for us and what we're going to do now is to understand how do you, what does the matrix look like if you're just doing a rotation about a single axis, a single rotation about a single axis. So hopefully you remember this example from before. This was our translation example, right? And we said that in fact, to transform the M frame into the C frame, we had to do -5 along the x-axis, 4 along the y-axis, and 1 along the z-axis. Of course, transforming the frame from M to C is the same as the homogeneous transform from C to M that will take a point and transform that. And we said for this particular example, this was the transformation matrix. And then we said for an arbitrary ABC, you get something like this, right? So here's an example that we did before where you can see we have two coordinate frames, the E coordinate frame and the H coordinate frame. And we want to transform the E coordinate frame into the H coordinate frame. So we look at this and we notice that the z-axis of both frames lines up, and so we said, well, to transform the E frame into the H frame, we need to do a rotation, a positive rotation around the z-axis, which will kind of make this E-axis go down here and the y-axis go down there. Did I say the E-axis? I meant the x-axis. Anyway, so the x-axis goes down here and the y-axis turns around here, so that we actually end up having what looks like H coordinates over there. And of course, the rotation that we needed was a rotation of positive 90 degrees around this z-axis. And how do I know it's positive 90? Because I stuck my thumb in that direction, and that meant that my fingers curled round kind of like that, and so it was positive direction. Do those look like fingers? Not really, but you get the idea, right? And of course, I was using my right hand to do that. So we ended up with the frame transformation from E to H was a rotate about the z-axis of 90 degrees. So of course, we want to know what's the matrix for this rotate z of 90 degrees that we could use to use for the T transformation to transform points from H coordinates into E coordinates. And we're just going to go straight to the generic, how do I rotate z by theta? What's the matrix that represents that? So, here is the matrix that represents an arbitrary rotation about the z-axis of theta degrees. So if this is the matrix for an arbitrary theta, we want to know what is the matrix for 90 degrees. So we need to remember those sines and cosines of common values, because most of the examples we're going to do are going to involve rotations that are 90 degrees, 180 degrees. So now is the time to start remembering what those are. And of course, for this example, if we remember our unit circle, let's see, can I squidge this and put it up here? If you remember our unit circle, and we start there, and there's 90 degrees, And so we're going like this. And remember that sine is the vertical value here, and cosine is the horizontal value. Well, if we rotate it all the way up here, then we've dropped a perpendicular, then our cosine is going to be 0, and our sine actually goes all the way up to the end of the unit circle, so our sine is going to be 1. So everywhere in this thing where we have cosine of 90, we can replace that with 0, and where we have sine of 90, we can replace that with 1. So this guy actually becomes -1. This guy is 0. So here is the final neat version of rotate Z90. And of course, that rotate Z90, we were figuring it out for the frame transformation from E to H, but that also represents the homogeneous transform from H to E that takes points in the H coordinate frame and turns them into points in the E coordinate frame. So let's use this matrix to do some sanity checks. If I want to transform a point in H coordinates into E coordinates, and I want to actually transform this point right here, the origin, well, what's the location of the origin in both coordinate frames? Well, it turns out that in the H coordinate frame, the location is 0, 0, 0. I'll just put the subscript on that to show that I'm doing this relative to H. And the 0, 0, 0, it's also going to be 0, 0, 0 of G, right? So this is a pretty obvious example, but it's a useful first step to just make sure that this matrix that I gave you actually works for something super simple. So basically what we're going to do is we're going to eyeball it and say, okay, I know that this should be the answer if I pre-multiply by this matrix, if I pre-multiply this point by this matrix, and let's see if we really get this as the answer. So we need to start with this matrix. And we're going to do a matrix multiply of that matrix by the origin, the point 0, 0, 0. And magic, when we do the math, we actually get the correct answer, right? So remember that since this matrix is our transformation, homogeneous transformation from H to E, this first 0, 0, 0 is actually in H coordinates, and the second one is in E coordinates, and it just so happens that their origins are on top of each other, so the value is the same. Let's do another sanity check where we just kind of eyeball this and say, here's another point. I've said that this point is 8, 0, 0 in H coordinates, and I want to know what is its location in E coordinates. So I'm going to do the same thing. I'm going to start by writing down my matrix transform from H to E. And then I'm going to take the point in H coordinates that I want to transform into E coordinates and pre-multiply it by this matrix. And if you do the multiplication, you get this answer. So the question is that really its location in E coordinates? So let's see, in E coordinates, the X is 0, and that makes sense because there's X is E is 0. The Y in E coordinates is 8, and yep, look at that, Y sub E is this axis, so that would be 8, and we expect the Z to be 0, so actually that looks pretty good. It's not a proof that it works, but it's a nice check. So let's just do another sanity check. Here is the point 2, 0, 10 in H coordinates, right? And let's see what we get when we transform that into E coordinates. So again, I multiply my point by that transformation matrix. And here's what we get. Again, that's the point in H. This is where I claim the point is in E. Let's see. So in E coordinates, the X part is 0, and that makes sense because there's the X-axis. E coordinates, this is the Y-axis, right? So we would expect that to be the 2, and sure enough it is. And this is the Z-axis, and that's the 10. So again, it looks good. It seems to be working. That's great. Of course, presumably the question you have now is what happens if it's not a rotation about the Z-axis. And it turns out that there's a transformation matrix, a generic matrix for what if it's a rotation about the y-axis, what if it's a rotation about these x-axis, and of course here's our original one for the translation matrix, and here's our z. Now, I'm not going to make you memorize these. You absolutely don't have to memorize these. You probably have already memorized the translation one. It's interesting to look at these and kind of see that I like to think of the columns as sort of new in terms of old. So, for example, if I'm looking at this Y matrix here, if I do a rotation of theta degrees about the y-axis, well, the y-axis is still aligned in exactly the same place as it was with itself, but the x-axis changes by cosine theta and negative sine theta, and the z-axis changes, the new z-axis changes by the sine and, the cosine. If what I just said makes no sense to you, then forget it. All you need to know is you don't need to memorize these. But it's kind of useful if you look at one of these rotation matrices. If you're rotating about z, then there's always going to be a 1 there. If you're rotating about x, there's going to be a 1 in the sort of x position of the unit matrix, right? If you kind of think about that part of your unit matrix, right? And if you're doing a rotation about y, this guy ends up like that. So just to wrap up, right now we can figure out the frame transformation and therefore the homogeneous transformation matrices for any combination of translations, right? Or for a single rotation about the x-axis or the y-axis or the z-axis. And what do we want to be able to do? Well, we actually want to take any arbitrary sequence of rotations and translations and figure out the F and T matrices for that. And that's going to be our next slide set.